Hey, welcome back to Fat Mama Physics. In this video, we are going to talk about exponent laws. This is exponent law number 1, section 2.4 in unit 2. We're going to cover product of powers and quotient of powers. So, of course, the company board game I chose for this one has to do with the fact that I decided to pick a game in which you have to or there's some mechanic in the game where you have to break down something into its components and count the individual parts by itself, because oftentimes when students do exponent laws, they tend to forget when to do it this way, when to do it that way, and the one way we could all use to remind ourselves which way is the correct rule is to remind us what is the basic meaning of exponents, which we'll talk about later in this video. So here we go. Let's show you about a game that has to do with breaking something into its components and counting up the individual parts. So let's give it a go. All right, so what we have here is a game called Oh My Goods by Alexander Pfister. He is a great, he's a very popular designer. He does a lot of great games. And this is a great two-player game, especially for me and my husband. We'll just like to duke it out sometimes. This game has to do with making goods, collecting goods, and making money. And of course, the person who does the best job of that at the end of, I believe, 8 rounds or whatnot, wins the game. So, every person starts off with a basic coal factory, and you might notice this is, I believe, German, has some, it first came out in the UK, so, which is why, I think, yeah, we even bought this, did we buy this in the UK? Oh, did we buy this in France? I don't remember, we might have bought this in France, I think, and found an English version. I don't remember. But anyways, you see some different languages here, which the top, I think it's German. So anyways, everyone starts with a basic coal and 7 components, which represent 1 piece of coal at a value of $1 each. Every person notices a little bit asymmetric depending on what you start with. So let's kind of break down what this means. So given a specific production plant, this is the amount of resources, the resources you need in order to start the production, and you may, from your hand, dump in as many of this resource to produce more coal if you like to. So this is called a chain if it's coming from the right side. This thing down below is in your assistant, the assistant who's going to run the particular factory. If it's 2 here, it means that you should be able to fully have all the resources, so he does a good job and essentially produces you 2 coal in addition to any chain that you would like to add. And chaining is not a requirement here. That's a bonus. Of course, if you're lacking resources for any reason, that's what this means. You only need, you require 1 less resource to make the production happen, but you only produce 1 coal from your base resource here. Okay? So, every person starts with some amount of hand cards, and just be interesting about the game itself in terms of production is the chaining process. So, for example, notice that this is a mill. Every single car has a dual purpose. One purpose is to produce this particular thing, so that's the resource. And this cart also functions as something that you could build. So you want to choose carefully what you want to use a resource and what you want to keep later to build. So here we have a mill, and of course, there's some chaining involved. Here we have a bakery in which the chaining process involves a coal and I guess this is flour that you would have produced over here. So I actually stacked up this hand, so that's very nice. Usually it's really rare that you get these nice chains to start your hand off and to determine the rest of your game. So this is interesting because what this person could have later is if this person had this card out and let's say had a set number of resource underneath this factory here, then when this person has this built, then whenever these resources on the left are fulfilled, this person can get, and it has to come as a pair, one coal and one flour to add under here. And notice that it increases the value of each of these individual products, which these were 2 each, and now they stack up. They become 4 each. So every single resource here becomes the actual value, or becomes 1 bread, essentially what that is. But they must come in a pair. You can't just take all, let's say you have no coal, you can't just use all of this to convert that into bread. You must have a pair, but each of those items become a bread. So notice the coal is only one worth of $1, but that becomes $4. So the chaining process is a very highly lucrative part of the game. Okay, so that's and of course, let's say the person had had the assistant here, and they produce very well, which I'll explain where the resource you get them in a second. So that's 2 of them here. Usually it would come from the hand or somewhere else, but anyways, here we go. And let's say they did this one action. So let's check how many cards. 1, 2, 3. There's 3 more of these. So I could pair that up with 3 more of this coal here. And that becomes a 6. 6 times 4 is 24. That's pretty good. There you go. So that's how much bread I could have in that one turn by using that chaining process. Very lucrative indeed. Okay, so how do I get the resources? Sometimes it comes from the hand, and the other mechanism is essentially what's available for grabs during the day. So after the players draw their hands and everything, we flip over cards. And this card doesn't have it, so I'm just going to keep flipping cards over until, see at the corner here of this card, there's a little sun. It means that marks the afternoon phase. So the morning is done, so then the players make some decisions, what buildings to build, etc., and then we draw more cards. Oh, that's it. That's the only one resource. This signifies the end of the day with another sun, and this is the only resource available for the time being. I think it's 2 sun. I don't remember. Sorry. That's a ruling detail I have to figure out. But that determines how many resources you could have. So, for example, if this were the case and the person was trying to run this, he or she would not be able to do that because this person needs 3 more wood from the hand to supplement that resource. Okay? So, that's essentially the game. So, how does this relate to exponents and count, and the fact that you have to break down something and count all its individual pieces? Now, remember when I said this bakery needed flour and coal. A pair of them becomes 2 bread, or each of these cards become a resource stacked under this pile over here. So that means if I want to count the total amount of bread, I just need to count how many cards in here to say how much I have or how much this is worth. So this is 1, 2, 3. This is inefficient here. So I have 10 cards. That's $40. That's pretty lucrative. Let's see what my winning point score was. I had a winning point score. A lower side is 30, could be up to 50 or whatnot. So 40 is pretty reputable. So notice that even with one turn, this chain pretty much is your game. So that's how powerful it is, and it's really fun that way. Okay, so count up the parts and count up the parts, and then do your summing process. Okay, so you always break it down and count them up. Break them down, count them up. Break them down, count them up. So let's see what this has to do with this particular section. Perfect! So I will clean this up later because I don't want to take up more time. So there is oh my goods. Oh my goods. Alright, so let's see what all of that has to do with exponent law number 1. So let's have a scenario here where we have 2 exponents or 2 powers that are multiplying one another. Okay, so specifically like that. How can we simplify it? And you might be wondering, this is stupid. I can just put this into my calculator and just figure out the answer without having to apply exponent laws. And I agree with you. It does seem a little silly because there's no application here. The application comes a little bit later, especially if you have to deal with exponents or dealing with variables. Like, for example, if I have x to the power 5 and I multiply that with x to the power of 2, then there's definitely a way to simplify that to make your life a lot easier instead of just having that separate. Now, these two things you cannot put into your calculator to evaluate the final answer. But if you put them together, you might save your life down the road in terms of calculations. So it's good to learn the skill. It's good to learn what to do in this scenario. What we do is, it's as simple as we add the two exponents. Okay? So in this example, we have -7 as the base and 3 and 5 as the exponents. We add the two exponents and slap that the sum of the exponents as the exponent of our new as the exponent of -7. Careful, they do have to have the same base, but then you just add the exponents to give you your new number. So let's say you didn't know what the number was. You didn't know what the base was. So all we have to do here is I would keep my base, and then 5 plus 2 is 7, so that I can simplify this and say this is x to the power of 7. And you might be thinking, oh, that's easy. Why would anyone confuse this with another rule? Well, there's more than one exponent law. So why does this work? Well, think about this. We know that -7 to the power of 3 is essentially 3 -7s multiplying one another. We're going to multiply that by -7, all of that to the power of 5 here. And that means I take -7 and I multiply itself 5 times. So here we have 1, 2, 3, 4, 5. So I'm still multiplying more -7s. But if I could just combine everything together, couldn't I just count the number of -7s I have and then say that's my new exponent? I have 1, 2, 3, 4, 5, 6, 7, 8. And of course there would be 8 -7s because those are the numbers dictated by the exponents in the previous multiplication sentence. So my new number, or my new way of expressing all this, is -7 as the base to the power of 8. So this is why the product of power works. Okay? So whenever you get your rule confused, if you're not sure, go back to what the original multiplication sentence means. Go back to the basic understanding of what an exponent is. What does it do to the base? So once you have that established understanding, then you can always refer back to that if you get confused what exponent law to use. Building off of the product of powers, the quotient of powers is something very similar. If you never heard of the word quotient, it just means the answer of two things that you divide. So the product is the answer of two things you multiply. The quotient is the answer of two things you divide. Okay? So as opposed to multiplying, so in our previous case, I had x to the power 5 and x to the power 2 multiplying each other. By the way, if they're stacked side by side, that immediately means they're multiplying one another. But what happens if I have something that looks like this? Okay, x to the power 5 divided by x to the power of 2. And from now on, we are used to the division symbol. But I wanted us to get used to division being a bar. Okay, being the bar, just like you would express a fraction, and that bar meaning division. Okay, so similar to the top, or actually not similar, in the opposite of what we do in the top is, as opposed to adding the exponents, when we divide these powers, we subtract the exponents, and it has to be in a correct order, because remember, division, subtraction, they both are order dependent. Okay, so what we have to do is we have to take the first exponent minus the second exponent. If I use my x example here, this would be x, the top minus the bottom. So 5 minus 2, this is x to the power of 3. And in their example, this is 7 minus 4 equals 8 to the power of 3. And why does this work? Same idea, okay? We take the basic understanding of what a power is. So 8 to the power 7 means 8 times itself 7 times. So I should find 7 eighths on the top of my division, and then the bottom I should find 4 because I have 8 to the power 4. And since I have 8 to the power of 4, then 4 of the 8s on the bottom is going to cancel exactly with 4 8s on the top of my division sentence, leaving me with whatever 8s are remaining, 1, 2, 3. Therefore, I have 8 to the power of 3. Okay, so that is the quotient of powers. All right, so if I have to summarize this up here at the top, if I multiply powers, okay, this becomes adding their exponents, okay? If I divide powers, then essentially that means I'm subtracting their exponents. And of course, always subtract first minus second. Order is important. So now knowing this, let's do some examples. Okay. Now, in this particular unit, many times you will see the instructions telling you to express as a single power. Because when you see this sentence, you are tempted just to put that into your calculator. And yes, it totally makes sense. It's the easiest way to do it. And why not use the easiest way? But the instructions say you have to express a single power to using your exponent laws before you evaluate. So that's important, and you'll actually lose credits for not doing that. So please read the instructions carefully in this unit. Okay, so let's go. We have 6 to the power 5 times 6 to the power 4. Both have the same base, so we can apply the exponent laws. We will have the same base of 6, and since it's multiplying, this is 5 plus 4. I get 6 to the power of 9. Okay, so there you go. That's our first example. How about this? I would like you to give B, C, and E a try. When you come back, I'll do those 3 examples first, and I'll do D and F last since they look a little trickier. Good time to pause the video. Alright, so let's go. Let's start with B. So I have -9. This is division. So that's 10. I have -9 as my base. I get 10 minus 6. This is going to be -9 to the power 4. Okay? Oh, and you know what? I totally forgot. I have to evaluate this. And even if you forget to evaluate it, I actually don't mind that as much because I know you can put this into your calculator. Actually, speaking of calculator, let's reinforce how we would use our calculator here. So if I have 6 to the power of 9, don't forget our little symbol here. That is the one that we use for power. So 6 as the base, 6, press that button to the power of 9. That's a very large number. Okay, and then next up I have -9 to the power of 4. I actually don't even care about that negative sign because I know it's to an even exponent. My answer is definitely going to be positive anyway. 6, 5, 6, 1. There you go. Okay, so let's do the rest here. This is multiplication again, so perfect. I just have to add the exponents at the top. And this is -2 to the power of 11. And putting this into our calculator, this is an odd exponent. So I'm actually still going to put it in without the negative because that's very annoying to do. It takes up time. And I just have to slot in my final answer is -2048. So yes. So did you know when you go to for gigabytes and terabytes and all those little things that you use for the computer actually has to do with the base of 2 to the power of something. So 2 gigabytes is actually 2048 bytes. So binary. All right, last one, E. This is division. So, whoa, that looks very similar to something we've done. So that's 5 minus 2. That's going to be -7 to the power of 3. And then we're going to evaluate this. And again, I know my answer is going to be negative. So I get negative 343. 343. Okay. Oh yes, always good to box your answer at the end. It's really helpful to help keep track of work. And of course, I will do D and F as more of a break. I'll do it slower than the other questions. Okay, so let's do D. When you are dealing with D, or anything where you have a combination of a multiplying division, of course, BEDMAS is always going to be in effect. So let's follow BEDMAS, which division comes before multiplication. So we're going to have to do this first. Okay, so doing that first means that we're going to have 3 to the power 2, and then this is going to be multiplied by, well, we know 4 minus 3, that's going to be equal to 1. So 3 to the power of 1 looks like that. And then we do multiplication, which then I get 2 plus 1, because it's multiplying, 3 to the power of 3. And that's just going to be 27. Okay, so using exponent laws first and always following BEDMAS. Okay, and last but not least, actually, is there anything I want to say before that? Nope, I think that's it. In the top example, the D, we actually didn't quite matter about the order since the it's all mashed up together. But it's always good to just follow the order just in case. Next but not least, let's do F. Oh, this is interesting. Now, you might say that, 9 to the power of 0 is going to be 1. So this is just, this 9 to the power of 4 divided by 1, that's just itself. It's very tempting just to write that, but let's still show that using exponent laws. So this will be 9, and since it's division, we have 4 minus 0, which is just 4. And that's just 9 to the power of 4, which is exactly 9 to the power of 4 divided by 1. Okay, you're right, but you do want to show your exponent laws anyways. So let's evaluate that. 9 to the power 4, we get, I think we did it before. I'm just being silly. 6561. Oh yeah, 6561. Okay, so there we go. That's the end of this page, which I'm gonna call the end of the video, but, ooh, I see. Actually, you know what? Whatever I'm going to talk about will be featured in the next video. So stay tuned for part 2 of Exponent Laws number 1, section 2.4. Thank you for watching. Good luck, Fat Mama Physics. Signing out.